In this video, we'll be looking at how to properly draw Lewis structures for molecules. And the reason why Lewis structures are so important is Lewis structures end up giving us a basic representation of the bonding and the valence electrons in our molecules. This is the very start of our unit on bonding, and the first way to kind of represent that bonding in a molecule, what's holding all the atoms together, is with Lewis structures. So what Lewis structures do is they represent that bonding and those valence electrons in a very simple picture, a very simple diagram. And we care about the valence electrons. Those are going to be the most important electrons for us. And these are the most important electrons because it's the valence electrons that are farthest away from the nucleus. Those electrons that are farthest away from the nucleus are those that are going to be involved in bonding. So that's why we care about these valence electrons so much. And you don't have to go through and write electron configurations every time you're trying to figure out valence electrons. Remember that you can quickly figure out how many valence electrons by looking at the periodic table. Remember that valence electrons match the group numbers using the old group numbering system. If your element is in group 1A, you're going to have one valence electron. 2A, 2 valence electrons. 3A, 3 valence electrons. On and on, 7A, 7 valence electrons. So all you need to do is take a quick peek at the periodic table to figure out how many valence electrons an atom is going to have. We've kind of seen this slide before. It's just a periodic table, but the thing we want to kind of pick out are the group numbers using the old group numbering systems. 1A, 1 valence electron. 2A, 2 valence electrons. 3A, 3 valence electrons. 4A, 4 valence electrons. 5A, 5. 6A, 6. 7A, 7. 8A will have 8 valence electrons in there. So you can just quickly peek at the periodic table. You don't have to worry so much about the transition metals. These are in the middle of the periodic table, all of the B's. We're not really going to see them involved with bonding and sharing of electrons, so we don't really need to concern ourselves with those. So now we kind of want to go through a sequence of steps for writing Lewis structures. And there's lots of different techniques you can use to write Lewis structures. This certainly isn't the only kind of technique. I like this technique because it gives you a set of checks that you can do. And with those checks, you can pretty much guarantee yourself that you have written the correct Lewis structure. So this is going to be the sequence of steps that we're going to use as we are writing through our Lewis structures. And we're just going to do example after example after example to kind of illustrate using this sequence of steps. And again, this sequence of steps is very, very useful because it provides some checks. You can look at what you've drawn and using these checks, know that you have the correct Lewis structure. There's no guesswork. There's no kind of indecision. These rules are going to get you to that correct Lewis structure. So now we want to use some examples to illustrate these rules. So the first molecule that we're going to draw is CF4. And the very first thing you do when you do a Lewis structure is you determine how many total valence electrons the molecule has. Because if your Lewis structure is a representation of the bonding and the valence electrons, you have to know how many you're dealing with. So we would look at the periodic table. We have 1 carbon and we have 4 fluorines. Well, looking at the periodic table, carbon has 4 valence electrons. Each fluorine has 7. So in our molecule, we're going to need 32 total valence electrons. So that means our molecule needs to show 32. Now, our next step is we determine what the central atom is. And that's because for most of our molecules that we're dealing with, they're not written in linear chains. Instead, usually what we find is that you have one central atom and then the other atoms surround that central atom. So how do we determine that central atom? Well, usually it's the first element listed. Hydrogen is going to be an exception to that. We'll see some examples of hydrogen a little bit later on. But here in CF4, carbon is our first element listed, so we're expecting carbon to be that central atom. So we're going to place carbon in the middle, and then we're going to arrange the fluorines around that central atom. It doesn't matter how you arrange them, kind of geometrically, spatially, in a two-dimensional Lewis structure. Later on in the unit, we'll talk about how to use the information encoded in these two-dimensional Lewis structures to get at how these molecules actually look in 3 dimensions. So that's our next step. We figured out the central atom, we place the outer atoms around the central atom. Now, the next thing you want to do is to actually start showing the bonding that has to happen. There has to be something connecting those outer atoms to the central atom. That's our chemical bond. And the way we represent chemical bonds in Lewis structures are with lines. So we're going to place a line between each central atom and that outer atom. And what that line represents, anytime we write a line in a Lewis structure, that represents a bond. And that means 2 electrons are being shared. Anything that gets placed between the 2 atoms represents something that's being shared. So we showed the connections. Now our next step is we still have a lot of electrons to write out in this structure. Remember, I just placed 8. I wrote 4 bonds, 2 electrons in each bond. That's 8 electrons that we're looking at. I have 32 total, so I still have a bunch more to get placed. The next thing you want to do is to start making what we would call lone pairs on these outer atoms. And the way we represent a lone pair is with a pair of dots. So what we're going to do is we are going to make 3 lone pairs on each one of our outer atoms. So starting with the fluorine on the left, I'll make 3 lone pairs. I'm going to represent them with pairs of dots. The reason why we're writing 3 lone pairs, we're going to see, is that that's going to be important for our, what we would call the octet rule. Many of our atoms in these molecules are going to have 8 electrons in their general vicinity. If we look at this fluorine on the right now there's 2 in its general vicinity. The 2 from the bond. To get up to 8, we would need 3 more lone pairs, or 6 more electrons to bring that total up to 8. These lone pairs are always going to come in pairs. You're very rarely going to have any sort of isolated electrons. They're almost always coming in pairs. So whenever you write a pair of dots, I'll show this in blue on the bottom, every pair of dots that you write in a Lewis structure is a lone pair, where each dot represents an electron, and they usually are coming in pairs. Notice where I place these dots around the fluorine. I didn't place them in the space between the central atom and the outer atom. That's because these lone pairs are not being shared. They belong exclusively to that outer atom. So now, the most important things you can do in any Lewis structure is to check to see if you've done things correctly. So the first thing we want to do is check to make sure that we have 32 electrons in this structure. Do we have 32? So you want to go through and count up those 32 electrons. So 2, 4, 6, 2 from the bond make 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I do have 32 electrons in that structure. So that check worked out correctly. We have 32 electrons in there. The next thing we want to do is to check for that octet rule. Most atoms are going to follow the octet rule in our Lewis structures. So what I'm going to do is we're going to check each of our atoms. So if I look at this fluorine on the left, does that have 8 electrons around it in its area? 2, 4, 6, 8. Yes. Now if I check the other fluorines in the same way, if I check the fluorine on the bottom, the fluorine on the right, the fluorine on the top, they should also all have 8 electrons in their area. We can see that they do. 2, 4, 6, 8 around that fluorine. Fluorine on the right, 2, 4, 6, 8. Fluorine on the top, 2, 4, 6, 8. So we see all the fluorines are good with their octets. The last thing we would have to check is we would also check for the octet around the central atom. So we'll kind of clear our counting marks here. And now if we look around that carbon, does that carbon have 8 electrons in its area? So if I look around that carbon, do we have 8 electrons in its area? You can count them up. 2, 4, 6, 8. Yes, that carbon also is satisfying that octet rule. When you have both of those checks working out, the correct total number and the octet rule, then you can rest pretty well assured that you have the correct Lewis structures. That's why you always want to do those checks. Are there sometimes going to be exceptions? Yes, we're going to kind of go through those exceptions a little bit later with some examples, but that's always how you want to start kind of dealing with these. So our next example that we want to look at is NBr3. And each Lewis structure you want to go about the exact same way, same sequence of steps. First, we want to figure out how many valence electrons we're really dealing with. We have 1 nitrogen and 3 bromines. Nitrogen is in group 5A for 5 valence electrons. Bromine is in group 7A for 7. So we're looking at a total of 26 electrons that we would need to have in place for our valence electrons. Next, we would determine the central atom. Usually it's the first one listed. So we'd have our nitrogen as the central atom. We'd have the bromines as the outer atoms. And again, it doesn't matter how you arrange the bromines around the outer atoms. I could have done it like this. I could have made them equidistant from each other, evenly spaced out. I could have put something on the top. It doesn't matter in the two-dimensional Lewis structure how you position the atoms. The two-dimensional Lewis structure in and amongst itself is not trying to convey three-dimensionality. That's something we'll talk about later, is how to take these two-dimensional Lewis structures and tell how these molecules look in 3 dimensions. So now we have our central atom, we have our outer atoms. We can make a single bond connecting each outer atom to the central atom. After all, there has to be something holding these atoms in place. Next, just like previously, we would start making lone pairs on each of our outer atoms. So that would be 3 lone pairs on each outer atom. So starting with the bromine on the left. And the reason why we're making these lone pairs, that's going to help us satisfy the octet rule. So 3 lone pairs around each outer atom is what we're looking at. Bromine on the right, same thing, 3 lone pairs. And remember, the lone pairs are not going to be positioned in that space between the two atoms because these lone pairs belong exclusively to that specific atom. They're not being shared. So now we're ready to go through our checks. And our first check is to check for our total number of electrons. We counted out 26 in our first step. Do we have 26? Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. The answer is no. We only have 24 electrons in our structure. We need 26. That check is failing. When this happens, you don't even need to concern yourself with the next check of dealing with the octets. You got a problem to deal with before that. You're short electrons. You only have 24 in your structure. You need 26. So how do you fix this? The situation that we're in is we need more electrons in our structure. We don't have enough. The fix for this is it's at this stage that you can start placing lone pairs on the central atom. So being we're short 2 electrons, where can those go? Well, now we can make a lone pair on the central atom. So we're going to make a lone pair on the nitrogen now. Now, just because you did that step, don't assume everything now is fine and perfect. The last things you should always do in a Lewis structure is those checks. They're pretty much your guarantee that you did that Lewis structure correctly. So I'm going to go back and do those checks again. Always end on those checks. Well, previously already kind of marked off in yellow, we counted up 24 electrons. Well, we needed 26. Do we have 26? Yes. Those lone pair, that lone pair that we put on the nitrogen got us up to the correct total. But remember, there's still another check we need to do. We still need to check for the octet rule. So you still have to go through both checks. Always end with the check. So now we want to go through and check out our octet rule. So we're going to start with the outer atoms for our check. So I'm just going to use some red to kind of group things so we can easily look at them. So I'm looking around each one of our outer atoms, the bromines. And then we say, do we have 8 electrons in that atom's general area? Well, 2, 4, 6, 8. Around the bromine on the left, the answer is yes. If we look at the bromine on the bottom, 2, 4, 6, 8. That's also a yes. The bromine on the right, 2, 4, 6, 8. So all the bromines are good with their octets. Next, we would also have to check our central atom out, because the central atom we're going to try to follow the octet rule for as well. So now if we look at that central nitrogen, so if we kind of look around that central nitrogen, do we have 8 electrons around that nitrogen? So if you count those electrons out, 2 for the lone pair, bond 4, bond 6, bond 8. Remember, 2 electrons in a bond. We can see we have 8 electrons around that central nitrogen as well. So both of our checks worked. We have the correct total number of electrons and we have octets around everything. So when both of those checks end up working out, we can be pretty confident that we do have the correct Lewis structure. That's why you always want to end with those checks. Even if you use a kind of different sequence of events, a different technique than kind of the sequence of steps we've been using, please, please, please do those checks. They're pretty much your guarantee that you have done that appropriately. Now, as we look at our next example is SF2. And you just want to follow the same pattern, the same sequence of events. First thing is we want to total up valence electrons. We need to know how many electrons our structure needs. If you look at sulfur on the periodic table, it's in group 6A, so that's going to be 6 valence electrons. Fluorine is in group 7A. So our sum total that we're looking at is we're going to have 20 valence electrons in our structure. So now we're looking at, okay, pick out that central atom. Usually it's the first one listed. That would be the sulfur. That would make the fluorines the outer atoms. Remember, in the Lewis structure, it doesn't matter how you position the outer atoms. I could have left and right, I could have top and bottom, I could have them across the diagonal. It doesn't ultimately matter, because what we're going to see is that the three-dimensional structure is going to look kind of different than it looks in this two-dimensional representation of a Lewis structure. So we place the outer atoms around the central atom. Now we're going to make a bond connecting each outer atom with that central atom. So we made our bonds. Next we would, like we have previously, make lone pairs on our outer atoms. So that would be 3 lone pairs around each fluorine. Fluorine on the left would get 3 lone pairs. Fluorine on the right would get 3 lone pairs. Remember, I'm also making sure I don't place them between the fluorine and the sulfur, because anything you place between 2 atoms represents that they're being shared, and these lone pairs are not being shared. So now you would go through your checks. You want to count out your electrons. Did you put 20 in your structure? So if we count out the ones we have, 2, 4, 6, 8, 10, 12, 14, 16. No, we're short electrons. So don't worry about the octets. You got a bigger issue to fix. You only have 16 electrons in your structure. You need 20. So just like we saw in the previous example, when you need more electrons in your structure, where will they go? Well, those would go as lone pairs on the central atom. Here I'm short 4 electrons, so that would be 2 lone pairs. So I'm going to add 2 lone pairs to our central atom. Now I'm going to go back and do my checks again. Remember, you're always ending on those checks. So previously, you can see with the yellow marks, I've counted up 16 electrons. Do I now have 20? Well, 18, 20. Yes, now I have 20 electrons. So now I have the correct total number of electrons. Your next step is going to be checking out your octet rule. We'll kind of clear our counting marks for a total number. Now we're looking at counting out. Do we have an octet around each one of our atoms? Are there 8 electrons in its general area? So start with the outer atoms. So we look at the fluorine on the left. Are there 8 electrons in its general area? 2, 4, 6, 2 from the bond make 8. The fluorine on the right, 2 from the bond, 4, 6, 8. Yes, both of the fluorines have their octets, so they're good. Remember, we still have to also include our central atom in terms of an octet check. So if we look around that central sulfur, so if we focus our attention on that central sulfur, do we have 8 electrons in its general area? 2, 4, 6, 8. The answer is yes, we have 8 electrons around the sulfur. So the structure that we wrote satisfied not only the correct total number of 20 electrons, it had the octets set up correctly. Each element had 8 electrons in its general area. So we're pretty confident that this is our correct structure. Now in reality, this molecule kind of looks like everything's in a straight line. In the next chapter, we're going to see that it's really not in a straight line. The actual structure is bent. Not everything is in a straight line, but for your Lewis structure, you're not trying to directly show that three-dimensionality in that Lewis structure, so it's okay to leave it like this. We've seen that hydrogen can be an exception. If you look at your kind of rule list for writing out Lewis structures, you see that hydrogen can sometimes be the exception to things. So we want to do a couple of examples that show hydrogen as the exception, because hydrogen shows up in a fair number of molecules. We want to make sure we're representing that correctly. So first thing is always counting up your valence electrons. I have 1 carbon and I have 4 hydrogens. Carbon, when we look on the periodic table, is in group 4A. Hydrogen is in group 1A. So we would have a total of 8 valence electrons we would need to place. Next is determining the central atom. Usually it's the first one listed. Also, hydrogen can't be the central atom. That means we have no choice but to use carbon as our central atom, and that forces the hydrogens to be our outer atoms. Next, we're going to make a bond connecting each outer atom with that central atom. Now next, what you would normally do is you would normally now add lone pairs to the outer atoms to help them satisfy the octet rule. Hydrogen is the exception to this. Hydrogen doesn't follow the octet rule. Hydrogen follows what's called the Duet Rule. Hydrogen can't handle 8 electrons. Hydrogen can only handle 2 electrons. And if you look at any of the hydrogens, I picked the one on the left, hydrogen already has 2 electrons in its area, and it can't the 2 from the bond. And so it can't handle any more electrons. Being it can't handle any more electrons, you're not placing lone pairs on hydrogen. So when you have hydrogen as that outer atom, it doesn't get any lone pairs. It can't handle that many electrons, so you just go on to the next step. The next step is we're already at our checks. So we want to check to see if we have 8 total electrons in our structure. 2, 4, 6, 8. Yes, that looks good. Now next we would check for our octet rule. Well, we just talked about hydrogen not following the octet rule. Hydrogen follows the duet rule. Hydrogen only gets 2 electrons. Does each hydrogen only have 2 electrons? Well, yes, each hydrogen has the 2 electrons from the bond, and that's it. That's why we didn't place any lone pairs on there beforehand, because they can't handle any. 2, 2, 2, 2. That's all hydrogen can handle, so that's good. Now, just because hydrogen doesn't follow the octet rule, doesn't have 8 electrons, that doesn't now stop carbon from having to follow that octet rule. We still have to make sure that carbon is following that octet rule. So if we look around the carbon, do we have 8 electrons around the carbon? And when you count them up, 2, 4, 6, 8, the answer is yes. So we have the correct total number of electrons in our molecule. Carbon's following the octet rule, so that's good. Hydrogen doesn't follow the octet rule, it follows the duet rule, and it is. So we feel pretty comfortable that this is our Lewis structure for CH4. We want to do another example of kind of hydrogen being the exception to the octet rule. So a good one to do would be water. So for water, we have 2 hydrogens, 1 oxygen. Hydrogen is in group 1A, so that brings 1 valence electron in. Oxygen is in group 6A when we look it up on the periodic table. That means we're looking at a total of 8. Next, we would pick out the central atom. Usually it's the first one listed, except hydrogen. Hydrogen is not going to be the central atom. Remember, the central atom kind of serves as that central hub. It has quite a few electrons around it. Hydrogen can only handle 2 electrons in its area, so it can't serve as that central hub, that central connection point. That's why hydrogen isn't the central atom. Even though it's listed first, it's not the central atom. So if it's not hydrogen, it has to be oxygen. So oxygen in the middle, hydrogens as our outer atoms, make a bond connecting each outer atom with that central atom. Now we go through the same procedure. Normally we would complete octets around those outer atoms. The outer atoms are hydrogens, so they don't get any lone pairs. So next we would go to our checks. How many electrons do we have? Well, Right now we only have 4 electrons. So being we only have 4 electrons, we need 8. That means we're short electrons. Where will they go? Those electrons will go on the central atom. Now we go through and we do our checks. So when we go through and we do our checks, do we have 8 electrons now? Yes, 2, 4, the lone pair 6, lone pair makes 8. Now we're good on total number of electrons. Next we would check out octet rules. Well, hydrogen doesn't follow the octet rule. Hydrogen follows the duet rule. So if we focus on the hydrogens, is hydrogen following its duet rule? And the answer is yes. That hydrogen on the left has 2. The hydrogen on the right has 2. That's all it can handle, so that's good. We still need to make sure that the oxygen is following that octet rule, though. So if we look around the oxygen, do we have 8 electrons in oxygen's area? And the answer is yes. We could count those up. 2, 4, 6, 8. We're good with that. So we can be pretty confident that this is our correct Lewis structure. So we're feeling pretty good that this is our Lewis structure. Now, it's fine to write the molecule like that. What we're going to see in the next chapter, though, is that three-dimensionally, this molecule is not in a straight line. It's not linear. So a lot of times you will see water written kind of this way, trying to show its three-dimensionality. You'll see it written as a bent structure to try to represent how it looks in 3 dimensions. You don't need to worry about that right now. We'll talk about the three-dimensionality of these molecules next chapter. The next molecule we want to look at is SO2. And we're going to go through that same set of procedures that we've been using for our other molecules. So we're going to start by figuring out how many valence electrons we need total. So we have 1 sulfur, 2 oxygens. When we look at sulfur on the periodic table, it's in group 6A for 6 valence electrons. Oxygen is also in group 6A, so each oxygen will contribute 6 valence electrons. So we're looking at a total of 18 valence electrons. Next, we would determine the central atom. Usually it's the first one listed. So we would have sulfur in here as our central atom. Oxygens would be our outer atoms. Make a single bond connecting each outer atom with that central atom. Now we would complete octets around those outer atoms. So for each oxygen, we would start adding lone pairs, 3 lone pairs around each outer atom. So the oxygen on the left would get 3 lone pairs. The oxygen on the right would get 3 lone pairs as well. So then you would check and see how you have been doing. You'd start doing your checks. Do you have 18 electrons? Well, 2, 4, 6, 8, 10, 12, 14, 16. No, we're short 2 electrons. When we're short 2 electrons, what do? Well, we would add 2 electrons as lone pairs on the central atom. So we would add in a lone pair on the sulfur. So now when we count, we already had 16 accounted for. 2 more would make 18. So that's good. We now have the correct total number of valence electrons. Now we would have to look at our octet rule. So kind of erase our previous marks. So now when we're looking at the octet rule, starting with the outer atoms, if we look at the outer atoms, the 2 oxygens, we're going to see that both of the outer oxygens have their octet set. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. So if we kind of clear those markings, because we still have to check that central sulfur. When we check that central sulfur, we're going to see we're in a situation that we haven't been in before. When we check this central sulfur, and we count up those electrons, how many electrons do we have around that central sulfur? 2, 4, 6. Sulfur is not satisfying its octet, so we have to fix this. Now this is a different problem. This is a different situation than we were in before. It's not that we don't have enough electrons total. It's that sulfur doesn't have 8 electrons in them. So this is a different problem. This requires a different solution. We can't just add 2 more electrons as a lone pair on the sulfur. That doesn't solve that problem, because if we did that, we would have 20 total electrons. That's not fixing a problem. That is creating a different problem. So we can't just add another lone pair. This is something different because we have the correct whole number. There are 18 listed. We can't just add 2 more. What this means is that what we have is not arranged correctly. We have the correct whole number right now, but they're not arranged correctly. So the way to fix this problem, to give sulfur its octet, is you have to look at one of the outer atoms. And you're going to take a lone pair from one of those outer atoms and move it in to make another bond with the central atom. And it doesn't matter which outer atom you use or which lone pair you use. I kind of randomly picked the ones I did. And we'll see why it doesn't really matter coming up in a little bit. So I need to take that lone pair that I circled in red and move it in to make another bond with that central atom. So I'm going to have a double bond between the sulfur and the oxygen. Now I'm going to draw out the actual result of that. I'm going to leave everything else the same except for that change. So now I'm going to have a double bond between that sulfur and the oxygen. The one on the right will still show as a single bond. And now I'm going to make my lone pairs. Remember, everything else in the molecule is going to be the same except for that change that I made. So still having 3 lone pairs on that oxygen on the right. So the only change that I made is what I showed in red. I took that lone pair from the oxygen and went in and made another bond between the sulfur and the oxygen. And we just made a bunch of changes. You should always make sure that your structure is good. Always the last thing you should do is to do those double checks. So when you do those double checks, do I still have 18 electrons? So let's count them up. Do I have 18? 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, I'm still at my 18, so I'm still good. I erase those kind of highlight marks. We would then check that to make sure everything has its octet. Remember, that's what was giving us problems. So starting with the outer oxygens, do I still have octets set up for these? And the answer is yes. I still have my octets, which I need. 2, 4, 6, 8 electrons are on the oxygen on the left, oxygen on the right, 2, 4, 6, 8. So the oxygens are still good. Now I need to kind of look at that central sulfur. Remember, on the top, that's what was giving us problems. The sulfur didn't have the octet. Did we fix that problem? So if we look around that central sulfur, do I now have 8 electrons in its area? And the answer is yes, we do. 2, 4, 6, 8. We fix that problem. This bottom structure now satisfies all of our rules, all of our conditions that need to be met. We have the correct total number of electrons, and we also have octets around everything. So here's what we're looking at for that Lewis structure. And we're going to spend a little bit more time on this molecule because this molecule illustrates something that's called resonance. And what resonance is when two or more Lewis structures are needed to accurately describe the bonding of a molecule. When we think about these Lewis structures that we are writing, how are we representing electrons? Well, when we're representing electrons, we're representing the electrons with dots and lines. If we think about dots and lines, that's our most basic form of written communication, dots and lines. So using them to represent electrons, which we know are incredibly complex, has a limitation. And what we're going to see is sometimes we need more than one Lewis structure. And that's the idea of resonance. So we'll show that with SO2. And when we have multiple resonance structures, the key is that the molecule isn't switching back and forth between the structures. It never looks like any of the structures. It will always look like an average of those resonance structures at every moment in time. And we'll use SO2 to kind of show this idea of resonance. So if we go back to thinking about SO2, and I'm going to go to that point before we made the double bond. So if you kind of look back, we had a situation like this. Here's our structure. We then had our lone pairs in. So I'm just going back to that point before we made the double bond to kind of illustrate resonance. We were at this situation here, where we had the correct whole number of electrons, 18, but sulfur didn't have its octet. So what did we end up doing? We ended up taking a lone pair from one of the outer atoms, and we ended up moving it in to make another bond with the central atom. And that's how we ended up fixing that. So if I kind of draw that result kind of on the left, here is that kind of result that we ended up with from our previous slide. I'm just going to redo what we had. Put in the lone pairs. So now here in this structure we have on the bottom left here, we'll kind of label it with a red A. This is where we ended up on the previous slide. We said we were okay with that Lewis structure. But here's kind of the problem. That Lewis structure that we have labeled A doesn't accurately describe the bonding in the molecule. When you look at that structure labeled A, you see that one oxygen has a double bond to sulfur, one has a single bond to sulfur. Now bond lengths are different between a double bond and a single bond. So what that structure A is really saying is that, well, the oxygens are fundamentally different in this molecule. One's closer to the sulfur than the other. This doesn't match the actual reality. If you were to really zoom in on a molecule of SO2, you would see that each oxygen is equally spaced around that sulfur. One's not closer to the sulfur than the other. So structure A doesn't do a good job of representing that true physical reality. And that's where resonance structures come in. So go back to what we had on the top when I moved that lone pair shown with the red arrow and the red circle to make a bond with the sulfur. What if I would have made a different choice with that? I'll kind of show this in blue. What if I would have chosen the other oxygen? So what if I would have done this instead? Would that have also fixed the problem? I'll do this in the bottom right. This will show a little bit different structure. So if I draw this one out, I would have this as my structure once I put in the appropriate lone pairs. So putting in my lone pairs. So putting in my lone pairs, just making that change that appears in blue now. So now I have two kind of different structures. If I look at that structure on the bottom right, let's call it structure B. Does B still satisfy the requirements that we need? Well, the answer is yes, it does. There are 18 electrons in that structure, and everything satisfies the octet rule. We need both of these structures, both A and B, to completely describe the properties of SO2, because the true nature of SO2 never looks like choice A on the left, and it never looks like choice B on the right. What SO2 really looks like is an averaging between them. It takes both A and B to kind of represent the molecule. It's not switching back and forth between A and B. It never looks like A and it never looks like B. Instead, it always looks like an average of A and B. Because of the limitations of Lewis structures, writing dots and lines to represent electrons, resonance can be difficult to show with one structure. That's why we often have multiple structures to show that the real true structure is a combination of both. So when you have resonance structures, what we often do is we often, showing that they belong together, we kind of link them with a double-headed arrow to show that, hey, we truly need both of these to accurately describe the molecule. It never looks like A. It never looks like B. Instead, it will always look like an averaging, a combination of A and B. It's just with our limitations of static lines and dots, we have to write multiple structures to kind of convey that information. So that's what we're looking at when we're dealing with resonance. It takes multiple Lewis structures to actually convey the true nature of the molecule, because just one doesn't portray an actual correct representation of that. And they're not switching back and forth. It's not AB, AB, AB switching back and forth. It's not doing that. It never looks like A. It never looks like B. It will always, at every moment in time, look like a combination of A and B. And we represent that with these multiple resonance structures that we have. The next structure that I want to kind of write is NO3-, nitrate ion. Now, this is going to be another molecule that could have resonance structures. I'm not going to focus on the resonance structures because instead I want to focus on a different feature of the molecule, the fact that this has a charge to it. How do you deal with things that have a charge to it? You deal with it right at the beginning. So when I count up my valence electrons, I have nitrogen, oxygen, oxygen, oxygen. We know that nitrogen brings 5 valence electrons into the structure because it's in group 5A on the periodic table. Each oxygen contributes 6. But what is that charge telling me? That negative charge tells me what? That negative charge tells me I have 1 extra electron than just what nitrogen and 3 oxygens normally have. So I need to account for that electron. If I have a negative charge, remember, electrons are negatively charged. If I have a negative charge, I need to add in an electron. If I was at -2, I'd add in 2 electrons. -3, I'd add in 3 electrons. So really, I don't have 23 electrons here. I have 24 valence electrons that I'm going to have to place for this. Nitrogen brings in 5, oxygens, each one brings in 6, but I have to account for that charge. That charge, -1, means I have one more electron. You have to take that into account in your counting, and then that will ultimately manifest itself in the structure. Now, when we draw the structure for this, nitrogen would be our central atom, oxygens would be our outer atoms, single bond connecting each oxygen with the central atom. We would next complete an octet of electrons around each outer atom, so that would be 3 lone pairs around each oxygen. On the left, 3 lone pairs. The bottom one will have 3 lone pairs as well. The one on the right will also have 3 lone pairs. Next, we would kind of check and see how we've done. Do we have 24 electrons? The answer is yes, we do. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 24 electrons. So we have our 24 electrons in place. That looks good. Next thing we would do is we would check our octet rule. So if we erase our previous highlighting marks, next we would check out our octet rule. And we would start with our outer oxygens. We kind of group things around our outer oxygens. Are we satisfying the octet rule for each of our oxygens? The answer is yes. 2, 4, 6, 8. Bottom oxygen, 2, 4, 6, 8. That's good. Oxygen on the right, 2, 4, 6, 8. That's also good. So our oxygens are okay with their octet rule, but we also have to check out our central atom. We have to check out the nitrogen as well. So now if we focus our attention on that nitrogen, do we have 8 electrons in its general area? And the answer is no. 2, 4, 6. We're short 2 electrons. Not in total. We can't just add a lone pair. Same thing we saw for the SO2. We already have the correct total number, so we can't just tack on more electrons. We have to rearrange what we have. So to rearrange what we have, we would take a lone pair around one of the outer atoms and move it in to make another bond with the central atom. Now, this molecule would also have resonance structures, because I could pick the oxygen on the left, I could pick the oxygen on the right, I could pick the bottom oxygen. For this, I'm just going to show one of the resonance structures, because I don't want us kind of getting wrapped up on the resonance structures for this. I want us to focus on that negative charge. So when we move that one in, what would be our result? Kind of draw this on the bottom. So when we move that one in, now we would have a double bond. If I fill in all of my lone pairs, oxygen on the left would still have 2 lone pairs. Remember, the only change that you make is that lone pair becoming a multiple bond. Everything else in the molecule stays exactly the same. So then we would get the structure on the bottom right. So now you want to check, is this the correct structure? Yes, we could draw other resonance structures, but is this one of the correct resonance structures? The answer is yes, this is our correct structure. Why? Because we're going to have 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I still have my 24 correct total electrons in the molecule. We just erase our highlighting marks here, because now we're going to recheck our octets. Remember, you always want to do these checks. They don't take that long to do. They pretty much ensure that you are doing this correctly. So if I look at my outer atoms, are my oxygens set with octets? Yes. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Yes, all of my oxygens are okay. Now, I want to check that central atom out, because remember, it was the nitrogen that was giving us problems previously. Did we correct that issue? The answer is yes, we did. If we look around this nitrogen, how many electrons do we have? We have 8 electrons in its area. 2, 4, 6, 8. Now we are good. So we have the correct total number, everything satisfying the octet rule. Now, I didn't draw the other resonance structures that can exist for this, showing the double bond on the bottom option or the one on the right, because I still want to focus on that key part, that negative charge. When something's charged, there's one last thing you do in your Lewis structure, and you need to represent that charge. So when something's charged, generally what we do is we put the entire Lewis structure in brackets, and we put the charge outside the brackets to really reflect that, hey, this is not a neutral molecule, this actually has charge to it. So what we see on the bottom right would be one of the resonance structures for NO3-. So we already saw one exception to the octet rule when we dealt with hydrogen, and that's one of the more common exceptions. But there are some other exceptions to the octet rule that we want to kind of look at and deal with, because you will run across these as well. And I broke these into different categories. And the first category or class are called deficient octets. So these are situations where you'll have less than 8 electrons around that central atom. We've already seen this with hydrogen as an example, but it can happen for other elements as well. So in a deficient octet, these are situations where you have less than 8 electrons around that central atom. And you'll sometimes find yourself in this situation when you're dealing with elements in group 1A, 2A, and 3A. These elements will often have deficient octets, as many times they're not going to have enough electrons. Remember, things in group 1A are only contributing 1 valence electron, group 2A 2, group 3A 3. A lot of times you just won't have enough electrons in place in order to have an octet. And you don't run across these extremely frequently, but you do run across them occasionally, so we do want to do an example to show you how to deal with these. And the example we're going to do is BeH2 for our example. So we have beryllium, 2 hydrogens. Beryllium is in group 2A, hydrogen is in group 1A. So you see we're only dealing with a total of 4 electrons. First, determine the central atom. Usually it's the first one listed. Also, hydrogen can't be that central atom, so we would get our beryllium as the central atom, hydrogen as our outer atoms. Next, we would usually complete an octet around the outer atoms, but remember, we have hydrogen as the outer atom. Hydrogen can't hold any more than 2. That means we can't do that. We would be going right into our checks. How many total electrons do we need? 4. Do we have 4? 2, 4. Yes. Look at our outer atoms. Are they okay in terms of octet rule? Well, we see we have hydrogen as our outer atom. So we already saw that hydrogen doesn't get an octet. Hydrogen only gets a duet. Well, hydrogen on the left has 2. Hydrogen on the right has 2. That's what hydrogen needs, so that's good. Now when we look at the central atom, when we look at the central atom, BeH2, well, how many electrons do we have in beryllium's general area? You notice we'll only have 4. 2, 4. We have a deficient octet. When you have a deficient octet, you want to say, is that okay? You always want to, when you're breaking the octet rule, however you're breaking it, you want to say, is there a good reason to do that? And in this case, there is. So beryllium, we saw, is in group 2A. We saw our rule from the previous slide that things in group 2A can have deficient octets. And there's no way in the world I could get 8 electrons around the beryllium when I only have 4 total valence electrons. So the fact that beryllium is in group 2A means that us having a deficient octet here is okay. So when you have elements in group 1A, 2A, or 3A, they don't have to, but they may have deficient octets. So our example of BeH2 shows us an example of that. Our next kind of exception to the octet rule that we want to look at is the case where you have an odd number of electrons. If you've been following along, you've kind of seen that every molecule we've done so far has had an even number of electrons. That's because even number of electrons with the electrons paired up make molecules fairly stable. There are times, though, that some molecules do have an odd number of electrons, and this is how you deal with them in terms of the Lewis structure. So this is our second category, odd number of electrons. So this category is really a subset of the first group, the deficient octets. What we're going to find is that there's going to be less than 8 electrons. I put this in its own category, though, in its own group, away from the deficient octets, because you really deal with this and go about the writing of the Lewis structure in a completely different way than what we did with the deficient octets. So we'll talk through this, and then we will do an example of this. So to do this, what you do is you first imagine an extra electron. You literally add an electron that's not there. And the reason you do that is because then you can go through the whole process just like any other Lewis structure. And then at the end, what you do is you unimagine that extra electron by removing it from the central atom. And we'll kind of show you how that works with an example. So the example we have is NO2. Now notice this is not NO2 minus, this is NO2, nitrogen dioxide. So this is a neutral molecule. It's not charged. It's not nitrate ion. If it was nitrate ion, we'd see a charge there. So we just have NO2. So we have nitrogen and 2 oxygens. Nitrogen on the periodic table is in 5A for 5 valence electrons. Oxygen is in group 6A. So we would have a total of 17. An odd number of electrons. Now, whenever you find you're having an odd number of electrons, because these are fairly rare, these are not very common. First thing, make sure you're truly in an odd number of electron situation. Double check your math. Make sure you have the number of valence electrons correct from the group number. Make sure you have the correct number of each type of atom, because a lot of times people think they're in an odd number of electron situation when they're really not. They just miscalculated something. This truly is an odd number of electron situation. We truly are at 17 electrons. So when this happens, what you have to do is you have to imagine an extra electron to get you to 18. Why do you kind of go through this process of adding in an imaginary electron, then removing it at the end? Well, because that gets you to the right end structure every single time using the same rules you've dealt with for everything else. So now we're going to go through this the exact same way. Determine the central atom. It's nitrogen. Outer atoms are our oxygens. Make a single bond connecting each outer atom with the central atom. Next, you would start making lone pairs on those outer atoms, 3 lone pairs on each oxygen. Take care of the oxygen on the left. Oxygen on the right would get 3 lone pairs. Now we would check and see how we've done. Do we have 18 electrons? 2, 4, 6, 8, 10, 12, 14, 16. No. We're short 2 electrons. Where would they go? They would go as a lone pair on the central atom. So that would give us our 18 electrons now. If we recount them up, we would get 18. Next, we would check for our octet rule. So checking for our octet rule, we would erase the old highlighter marks. Now when we check for our octet rule, starting looking at the outer atoms. Check out the outer oxygens. Do I have 8 electrons around each of the outer oxygens? And the answer is yes. 2, 4, 6, 8. 2, 4, 6, 8. So those are both good. Now we would check our central atom. Erase our old highlighter marks. Now if we check our central atom out, do we have 8 electrons around that central nitrogen? You're going to see that no, we don't. How many electrons do we have? We only have 6 electrons, 2, 4, 6. So what will we do? We have the correct whole number, but the octet rule is not being satisfied. So what would we have to do? We would have to move in a lone pair from one of the outer atoms to make a multiple bond. And this molecule would also have resonance structures, because I could pick the left-hand oxygen or the right-hand oxygen. I'm just going to show one of the resonance structures because we don't want to get lost in the resonance and forget about this odd number of electrons situation. So we want to remain focused on this odd number of electrons situation. So I'm not going to show both resonance structures. I'm just going to show the one resonance structure. So I'll draw the result of moving those electrons in. Remake our lone pairs. So the bottom structure just shows the result of doing what we illustrated in red, taking a lone pair from our outer atom and making a multiple bond with that central atom. Now we check and see if we are okay. Are we okay? 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, we're okay with the 18. Now we would check our octet rule. If I erase the old highlighter marks, now let's go and check out our octet rule. So when we go through and check out our octet rule, starting with the outer atoms, oxygen on the left, oxygen on the right. Oxygen on the left does indeed have 8 electrons, 2, 4, 6, 8 in this area. Oxygen on the right, 2, 4, 6, 8 in that area. So the oxygens are good. Now we look at the nitrogen. So when we look at the nitrogen, we kind of highlight around that. Do we have 8 in its general area? The answer is yes, we do have the 8, 2, 4, 6, 8. So that's good. So now we got to go back and remember that, hey, we imagined one of these electrons. Remember, we had an imaginary electron. So one of those 18 electrons that we have in this structure isn't really there. Because remember, we imagined one. We imagined one at the beginning. Now it's time to unimagine one. Take one away. Which one do we have to take away? The one we're going to take away is from the lone pair on the central atom. So we need to remove one of those electrons, just one. This is going to be one of the rare times that we have an unpaired electron. Remember, one of those electrons wasn't really there. We imagined it just to help us with our other Lewis structure writing, but at the end, we have to get rid of that because we have to get back to our correct 17 electrons. So that imaginary electron ends up being one of the electrons that form the lone pair on that central atom. If you go back and check, everything is going to work out. 2, 4, 6, 8, 10, 12, 14, 16. Now the 1 makes 17. That's good. If you go back and check out your octet rule, you'll find that both oxygens are still okay. Oxygen on the left, still okay. There's 8 there. Oxygen on the right, still okay. But the nitrogen, look at the nitrogen. How many does the nitrogen have? The nitrogen will have 7. 2, 4, 6, and then the 1, a single electron, makes your 7. So you can see that technically nitrogen has a deficient octet, but remember, I kind of made this its own category because of the way you deal with it. This is an odd number of electron situation. And the easiest way of dealing with these odd number of electrons are to go ahead and imagine an extra electron right at the beginning of the process, and then remove that imaginary electron at the end of the process. And the one you remove is one of the electrons from the lone pair on that central atom. Now you might be thinking right now, okay, well, why would I go through this whole elaborate procedure of imagining an electron, then taking it away? Why not just deal with another way? You could deal with it a different way, but when you deal with it using other techniques, you run the risk of messing up something else in the structure. This is kind of a strange tool, but it's a tool that guarantees that at the end, you will end up with that correct Lewis structure. So the next category of exceptions to the octet are expanded octets. And these are going to be situations where there are more than 8 electrons around an element. So this is the largest class of exceptions to the octet rule. You see these fairly frequently. The deficient octets, the odd number of electrons you only occasionally see, you run across these expanded octets all the time. So there are 3 criteria that have to be followed in order to expand the octet, and we'll see this with some examples. The first criteria is the element must be in the 3rd period or below. Remember, our periods are our horizontal rows. So the element has to be in the 3rd period or below. 3rd period, 4th period, 5th period, 6th period. So, and that's because 3rd period and below elements have an n value of at least 3. To get n equal to 3, what that does is that gives you d orbitals to expand the octet. Because remember, if n equals 3, what can your values of L be? L could be 0, 1, or 2. L equals 0 is an s orbital. L equals 1 is a p orbital. If you think about the octet rule, well, you get 2 electrons from the s orbital, 6 total electrons can fit in a set of p's. That gives you your 8. That's kind of where the octet rule comes from. But if you have n equals 3, not only do you have L equals 0, which are s orbitals, not only do you have L equals 1, which are p orbitals, you also have L equals 2, which are d orbitals. That allows you to have the space to expand the octet. If we look at something like sulfur, write out the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p4. You don't see any d orbitals filled, but that's okay, Because even though an atom of sulfur by itself doesn't have any electrons currently occupying the d orbitals, those d orbitals still exist, and they can be used in bonding. The way to kind of imagine this in a non-chemistry way is right now you're kind of watching this video and you're not in your car. Your car still exists even though you're not occupying it. Your car is empty right now, but it can accommodate you. Those d orbitals exist even though there are no electrons in them. Your car still exists out on the street, out on your driveway, wherever you parked it at, even though you're not currently in it. Same thing with the d orbitals. They exist even if an electron's not in there for the atom by itself. So that's why the third period and below rule kicks in. The second criteria is that the element that has the expanded octet has to be the central atom in your Lewis structure. You're not going to see expanded octets for your outer atoms, just the central atom. And that third criteria is that there must be necessity. Just because you can expand the octet doesn't mean you should expand the octet. Only expand the octet rule when necessary. We'll use a car example again. Your car may be able to go 110 miles per hour. That doesn't mean you necessarily want to drive your car at 110 miles an hour down the street. There should be a necessity to do that, a need to do that. So we're going to do multiple examples with this expanded octet because you see these happen fairly frequently. So the first example we want to do is SF6. So we're going to do this just like any other Lewis structure. We have 1 sulfur, 6 fluorines. We would check out the position on the periodic table. Sulfur is in group 6A, fluorines in group 7A, for a total of 48 valence electrons that we would have to put into place. Sulfur is our central atom. Fluorine is our outer atom, so we would need 6 fluorines surrounding the central atom. Again, it doesn't really matter how you spatially put them in. Here's my 6 fluorines. Next, we would complete an octet of electrons around each outer atom. So that would be 3 lone pairs around each fluorine. So if we do this to all the fluorines, so making 3 lone pairs around each fluorine. Now we would check and see how we did. Do we have 48 electrons here? Well, count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. You can see already that I missed a lone pair here. Get that lone pair back in there. Well, recount. Now we were at 22, so I missed a set of lone pair, so now 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. And that's why you want to do these checks. It's very easy when you have a lot of different dots to accidentally have too few, too many. That's what these checks do, is you would quickly, if you made just a careless error like I just did, the checks would quickly show that for you right away. So I do have 48 electrons. That's good. I erase those highlighter marks. And now we're looking at figuring out our octets once we kind of get rid of the old highlighter marks. We'll start with the outer atoms. Looking at each of the fluorines, are there 8 electrons around each one of these fluorines? So if we kind of look at our outer atoms here, we kind of show electrons around each one of the fluorines. Do we have 8 around each fluorine? And the answer is yes, we do have 8 around each fluorine. 2, 4, 6, 8 around that one. Bottom one, 2, 4, 6, 8. Yes. One on the bottom right, 2, 4, 6, 8. Yes. 2, 4, 6, 8. Yes. 2, 4, 6, 8. Yes. 2, 4, 6, 8. All the fluorines are good. Now we'd have to check our central atom. We'd have to check out that sulfur. So if we kind of erase our old highlighter marks and look at the sulfur, what's happening with sulfur? Sulfur going to have an octet of electrons around it. So if we circle all of the electrons around that sulfur, you can see sulfur is going to have an expanded octet in this. We count up those electrons, 2, 4, 6, 8, 10, 12. So we have 12 electrons around the sulfur. Anytime you draw a Lewis structure with the expanded octet, you want to go back to that set of criteria we talked about on the previous slide and say, is it okay that this molecule, this atom in this molecule, has an expanded octet? So go through that set of criteria. The first criteria is it in the third period or below? If you look at sulfur, sulfur is in the third period, so it satisfies that criteria. Second criteria is it the central atom? Here, yes, sulfur is the central atom, so that's okay. The third criteria is there necessity to expand the octet? And here there's definite necessity to expand that octet. There is no possible way you can get 6 fluorines. That's going to require 12 electrons to bond to that sulfur using only 8 electrons. There's nowhere else you could arrange those electrons to make this bonding happen. So even though sulfur has an expanded octet, it's okay that it has the expanded octet because it's in the third period or below, it is the central atom, and there is necessity in order to do that. If we look at another example of the expanded octet, we're going to see that SF4 will also have an expanded octet. I have 1 sulfur and 4 fluorines. Sulfur is in group 6A for 6 valence electrons. Fluorine is in group 7A. So I'm looking at a total of 34 valence electrons that I am dealing with here. Pick out the central atom. Usually it's the first one listed. Get your outer atoms arranged around that central atom. Make a single bond connecting each outer atom with the central atom. Next, you would complete an octet of electrons by making lone pairs on those outer atoms. So 3 lone pairs around each fluorine. Fluorine on the left would get 3 lone pairs. Bottom fluorine would get 3 lone pairs. Fluorine on the right would get 3 lone pairs. The top fluorine would also get 3 lone pairs in this. So now we kind of go through, we count up our electrons. Do we have 34 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 20, 30, 32. The answer is no, we don't have 34 electrons. We're short electrons. Where would they go? They would go as a lone pair on the central atom. So now we already marked off 32. Those 2 extra ones would make 34. So now we have the correct total number of electrons. We erase those highlighter marks. because now we want to go through and check our octets. So if we check out our octets, starting with the outer atoms, so kind of grouping things by the outer atoms, each fluorine is going to have 8 electrons in its general area. 2, 4, 6, 8, 10, 12, 14, 16, or sorry, let's recount that. 8 for the fluorine on the left, 8 for the bottom fluorine. We're not counting total, we're just counting for each fluorine. Fluorine on the right, 2, 4, 6, 8. Fluorine on the top, 2, 4, 6, 8. So all the fluorines are good. Now, if we look at that central sulfur atom, so if we look at that central sulfur atom now, erase the old kind of highlighting marks here, and now we're ready to look at that central sulfur atom. Do we have 8 around that central sulfur? So here are all the electrons around the central sulfur. Count them out. 2, 4, 6, 8, 10. You see we have 10 electrons around that central atom. Each bond has 2, there's 4 of them for 8, and then the lone pair makes 10. So we have an expanded octet. Remember, anytime you have an expanded octet, you want to check and make sure it's okay that you have an expanded octet. Well, is the element in the 3rd period or below? Yes, sulfur's in the 3rd period, so the first criteria is met. Second criteria is it the central atom that has this expanded octet? The answer is yes, sulfur is the central atom, so it's okay that it has an expanded octet. Third criteria is necessity. Is there any other way you could do this where you wouldn't be expanding the octet? So when you kind of look at this, and you look at those 2 electrons as a lone pair, could you do anything else with these electrons in order to make the situation better? So maybe some things you could consider doing is maybe if you turn those into a double bond between the sulfur and the fluorine. Well, that's not going to work. That's going to make the problem worse instead of better, because if you did that, you'd have expanded octets on the fluorine and the sulfur. And fluorine definitely can't have an expanded octet because it's not in the 3rd period and it's not the central atom. Or maybe you say, well, maybe that lone pair could belong on one of the fluorines. Well, if you tried throwing another lone pair on one of the fluorines, you'd find too many electrons on the fluorine. Again, fluorine can't have the expanded octet. It's in the 2nd period. Also, it's not the central atom. So anything else you would do with that lone pair that's on sulfur would not help the situation. It would make it worse. So that means you kind of met the necessity clause for this. You had to have an expanded octet on that sulfur. There was no other way in order to go about and do that. I want to do one last expanded octet example, and this is for SBR2, and this really focuses on the necessity clause for this. Now, if you use a sequence of steps that we've been doing, you wouldn't find yourself in having to make a choice. But if you use other techniques, there's potentially 2 different structures you could write. You could write the structure on the left, call that A, or the structure on the right, call that B. Well, the structure on the left is where you would go if you just followed the kind of patterning that we've done. You would never write the structure on the right. But let's imagine you use a different technique. If you use a different technique to write Lewis structures, you may write structure B on the right. And when you would evaluate structure B, you would kind of say, okay, what's going on with this? Well, I would need 20 electrons. Do I have 20 electrons? SBR2 has 20 electrons. Are there 20 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yes. So that's good. Then you would evaluate the octet rule. So starting with the bromines, if we evaluate the octet rule, starting with the outer atoms in the bromine bromine on the left, bromine on the right, they're both good for their octets. 2, 4, 6, 8, 2, 4, 6, 8. That's both good. Then you'd look at the sulfur. So if you look at the sulfur, if we kind of look around that sulfur, and you count up those electrons around the sulfur, you'd say, okay, 2, 4, 6, 8, 10, 12. Well, I have an expanded octet. Is it okay that I have an expanded octet? Well, you'd say, okay, sulfur's in the third period, so I can have an expanded octet. That's okay. Is sulfur a central atom? Yes, that would make it okay. Where the structure on the right fails is that necessity clause. Is you didn't have to expand the octet here. Why? Because structure A shows that you could have arranged these electrons without expanding the octet. So what that means is that structure B is not the correct structure. It fails that necessity clause. The real structure is what you see for structure A. Now again, if you use the technique and the sequence of steps that, I kind of went through with you in this video, you would never even write structure B. Structure B wouldn't even be a consideration. But other Lewis structure writing techniques could have you write structure B, in which case you would have to kind of say, is there another way? Is it okay? Does it fit all of the criteria? You didn't need to expand the octet, even though it was a central atom, even though it's in the third period. You didn't need to. So structure B is incorrect. You really want structure A here. You only want to expand the octet when there's need to, when it's necessary. So the next thing we want to talk about in terms of Lewis structure writing is something called formal charge. And what formal charge is formal charge is a formal way of assigning electrons to an atom in a Lewis structure. And what formal charge is the number of valence electrons minus the number of formal electrons. And we can use this in order to write better Lewis structures. It's kind of a tie-breaking type thing we can do when we have two good Lewis structures that we're looking at. We can use this to decide what the real Lewis structure should be. But first we want to just do some examples of counting out formal charge so we can see how to do that. And I'm going to use an example of a molecule that we have already drawn. And I'm going to do CF4. I'm just going to quickly re-sketch what we had for CF4. We had this structure for CF4. I'll put in the lone pairs. We'd have 3 lone pairs around each of the fluorines. I'll re-put in those lone pairs that we have. And we did this example earlier in the presentation. So we're going to use this as a way of thinking about formal charge. I'll just kind of re-sketch out our valence electrons on the side. Carbon had 4, fluorine had 7. So now we want to talk about writing out formal charge. And formal charge doesn't mean fancy. Formal in this case means more of a formality. And what you do is every electron in the structure gets formally assigned to one of the atoms. So let's start, if we look at this fluorine on the left, every electron in fluorine's vicinity has to be formally assigned, officially assigned to an atom. Well, the lone pairs are easy. We're definitely going to assign the fluorine all of its lone pairs. So Formal electrons are what I'm counting up. 1, 2, 3, 4, 5, 6. All of those definitely formally get assigned to that fluorine. But what we want to do is we want to look at this bond. When we look at that bond that I'm pointing to in blue, there are 2 electrons in that bond. They're being shared between the carbon and the fluorine. But in terms of formal, official accounting, we have to formally assign one of those electrons to the fluorine. One of those would get assigned to the carbon. So of those 2 electrons, one of them we're going to assign to the fluorine. The other one we're going to assign to the carbon. We're basically splitting those 2 electrons and saying one belongs to each of the thing that they're being shared with. The same thing would happen to the other fluorine on the bottom. 1, 2, the lone pairs would definitely be formally assigned to that fluorine. In this bond, one of them would get assigned to the fluorine, the other one would get assigned to the carbon. The fluorine on the right, same thing. We count formal electrons. The lone pairs, 1, 2, 3, 4, 5, 6. That would be 6 electrons there. In that bond, one of them would be officially counted as fluorines, making it 7. The other one would be officially counted as carbons. The fluorine on the top, 1, 2, 3, 4, 5, 6. The bond has 2 electrons. One would belong to fluorine. That would make that 7. The other one would belong to the carbon. So when we look at the fluorine, notice for each fluorine we formally counted up 7 formal electrons. That matches the number of valence electrons that fluorine had. So that means we would say that fluorine, each one of them, fluorine's formal charge would be 0. Its formal electrons exactly matched how many valence electrons it had. So the way we write formal charge is each atom gets listed a formal charge. So I'll erase all of our counting here. And then I'll show how to write the formal charge for each of the fluorines. Because the formal electrons exactly matched the valence electrons, they had a formal charge of 0. So usually what you do is you put the formal charge, written small, in parentheses near each one of the atoms. So each of the fluorine had 7 formal electrons that matched the valence electrons, therefore the formal charge would be 0. Now for the carbon, central atom also counts in this. Remember, carbon doesn't have any lone pairs, but remember, whenever we had a bond, there were 2 electrons in each bond. One of those electrons got formally assigned to the carbon. One of those belongs officially to the carbon, the other one to the fluorine. So out of each one of the bonds, one of those electrons gets officially, formally put on the carbon. So that means carbon would have 4 formal electrons in this structure. Look at how that matches with the valence electrons. 4 formal electrons, 4 valence electrons, those match. So that means the formal charge on the carbon would also be 0. We put that kind of in parentheses with a small number. So here, there isn't any formal charge on any of the atoms. Let's go to another example of just counting out this formal charge that we have. So if we look at NBr3, I'll just re-sketch NBr3 for us so we can kind of look at it. Remember, nitrogen was in group 5A, bromine was in group 7A. So we had 26 electrons. If I re-put in the lone pairs that we had 3 lone pairs on the bromine, 3 lone pairs on the bottom bromine as well. And we had 1 lone pair on the nitrogen. Now, if I assign formal electrons to each thing, starting with the bromine on the left, well, the lone pairs are definitely going to count formally as bromines. 1, 2, 3, 4, 5, 6. Remember, it's going to get 1 from the bond, 7. Remember, 1 from the bond goes to the bromine, 1 goes to the nitrogen. Bromine on the bottom. 1, 2 lone pairs definitely belong to bromine. 4, 5, 6. 1 from the bond makes 7. Bromine on the right. Lone pairs definitely bromines. 1, 2, 3, 4, 5, 6. 1 from the bond makes 7. Notice how for the bromines, each one has 7 formal electrons, 7 valence electrons. So that's going to be a formal charge of 0. Now if we do this for the nitrogen, lone pair definitely belongs to nitrogen, officially assigned to that. There's 2. Remember, it's going to get 1 from each of the bonds as well. So it gets another one here for 3, another one here for 4, another one here for 5. So nitrogen has 5 formal electrons. It matches nitrogen's valence electrons. So all the bromines have 7 formal electrons. That matches the valence electrons. The nitrogen has 5 formal electrons. That matches nitrogen's valence electrons. So what that means is that the formal charge of every atom in this molecule is going to be 0. So I'll just erase our kind of counting numbers here. We'll put in the formal charge. So we said the formal electrons match the valence electrons. That means this bromine would have a formal charge of 0. Bromine on the bottom would have a formal charge of 0. Bromine on the right would have a formal charge of 0. And the nitrogen would have a formal charge of 0 as well. So our next example will be a little bit more interesting because here, not all of the formal charge will be 0. So we did SO2 previously. Sulfur had 6 valence electrons. Oxygen also had 6 valence electrons in it for a total of 18. And again, this molecule does have resonance structures, but just for the purposes of formal charge, we only need to look at one of the resonance structures. So I'm just going to draw out one of those resonance structures for us to look at. Put in our lone pairs that we have. We have a lone pair on the sulfur, and the oxygen on the right had 3 lone pairs in it. So now, if we just count out our formal electrons, we'll start with the oxygen on the left. The lone pairs are definitely going to be oxygen's electrons. So 1, 2, 3, 4. Now in terms of the bonds, remember bonds get split 1 electron to each member of the bond. So that means one of those electrons belongs to oxygen, the other To sulfur, same thing with the other bond. Remember, 2 bonds, 4 total electrons. 2 are going to go to the oxygen, 2 to the sulfur. So oxygen's going to have, on the left, 6 formal electrons. When we do the oxygen on the right, I'll do this in purple. 1, 2, 3, 4, 5, 6 from all the lone pairs. Those will definitely belong to the oxygen. But remember, the bond gets split evenly between the oxygen and the sulfur. So the oxygen on the right gets 1 of the electrons from the bond, so that makes 7. Notice we don't have a matching number anymore. We'll talk about what that ultimately means. Next up for the sulfur, though, count up its formal electrons. The lone pairs definitely belong to the sulfur, so 1, 2. Remember, it's also getting 1 from each of the bonds, so 3, 4, 5. Sulfur is going to have 5 formal electrons. Now remember what formal charge is. Formal charge is the relationship between the formal electrons and the valence electrons. If we look at the oxygen on the left, they match again. 6 formal electrons that we counted out in red matches the 6 valence electrons. So the oxygen on the left, writing this in green, will have a formal charge of 0. Looking at the oxygen on the right, we counted up in purple 7 formal electrons. Oxygen only has 6 valence electrons. So I have 1 more formal electron than valence electron. Meaning I have 1 more formal electron than valence electron. It's like I added an electron. Well, electrons are negatively charged, so being I have 1 more formal electron than valence electron, the formal charge of that oxygen on the right will be -1. It'll have a negative formal charge to it. When I look at the sulfur, I counted up sulfur's formal electrons in blue. It has 5 formal electrons. You compare those formal electrons to the valence electrons. Sulfur has 6 valence electrons. In our structure, it has 5 formal electrons. It has 1 less formal electron than valence electron. Well, it's almost like it lost an electron. It has 1 less electron than kind of the number of valence electrons that are originally brought in. So that means that sulfur will have a +1 formal charge. Now, that's not saying these are the actual charges. They're not. This is a covalent molecule. Electrons are being shared. This is just a way of counting up kind of formally, as a formality, what kind of happened. And we can see when I erase all of our counting marks that not everything ended up with a formal charge of 0. The oxygen on the left had a formal charge of 0, but the oxygen on the right has a formal charge of -1. The sulfur has a formal charge of +1. So they don't always have to be 0. We wanted to go through these examples of counting up formal charge because now we're going to see how we can use this idea of formal charge in order to write better Lewis structures. We can use formal charge in a tie-breaking type scenario. So now that we know how to write formal charge, we want to talk about how to use formal charge in order to write better Lewis structures. So here are some guidelines for using formal charge to write even better Lewis structures. And the first is that the sum of each atom's formal charge is equal to the total charge of the molecule or the ion. Second thing that we're going to see is that in general, the less, and this doesn't mean more negative or less positive, it means closer to 0. The less formal charge, the better. You want to shoot for 0, even though sometimes 0 isn't a possibility. Usually it's a good idea to avoid writing structures that have formal charges of plus or minus 2, 3, 4, 5. Generally, you want formal charge to be 0 or pretty close to 0. The other thing that we're going to see is that the formal charge should be consistent with electronegativity values. They should tell the same story, not be conflicting. So with these ideas, let's see how we can use this in order to break a tie. So we're going to have a couple different structures for molecules that are pretty equivalent, but we're going to see that with formal charge, we can truly decide which one is the correct one. And the first one we want to do is CO2. So for CO2, in the interest of time, I'm going to write out kind of two possibilities, and then we're going to evaluate them. So carbon and 2 oxygens, carbons in group 4A, oxygens in group 6A, for a total of 16 valence electrons that we would have in place. Now there's two different structures you could write for CO2. I'll kind of show each one of them, and then we'll evaluate them. So one possibility would be what I'm writing here on the left. You could have a structure that looks like this, with 2 double bonds. Or you could have the structure that we have, that I'm going to show on the right, where you have 1 single bond and 1 triple bond. So if I put in the lone pairs for that structure on the right, we would have 3 on the oxygen on the left, and just 1 on the oxygen on the right. Now, and we'll kind of label these. We'll call the structure on the left A, we'll call the structure on the right B. Now, when we look at A and B, these are both very, very similar structures. If we were kind of going to evaluate them, we wouldn't even start with formal charge. We would just say, do they have 16 electrons? Are they following the octet rule? And when you look at structure A, you would count out 2, 4, 6, 8, 10, 12, 14, 16 electrons. That's good. Structure on the right, B. Does it have 16 electrons? Yes, 2, 4, 6, 8, 10, 12, 14, 16. I have 16 electrons there as well. So they're equivalent in that respect, and they both have the correct total number of electrons, which is good. Next, we would probably evaluate the octet rule. So we would look at the oxygens. So if we were to look at the oxygens first, well, structure A on the left, oxygens both have 8, that's good. Structure B on the right, you count up total number of electrons, they both have 8, that's good. Next, you might compare the central atoms. Are they following the octet rule for the central atoms? And you'll see that in both cases they are following the octet rule. Structure A on the left, 8 electrons are on that carbon. Structure B on the right, 8 electrons are on that carbon. So far we have a tie. They both have the correct total number of electrons. They're both following the octet rule. This is where you can use formal charge to break that tie. So if we go through and we assign formal charge for each atom in this structure, starting with A, the oxygen on the left would have a formal charge of 0. Why? Because it has 6 formal electrons matching its 6 valence electrons. The carbon on the right in structure A would have a formal charge of 0. 6 formal electrons matching its 6 valence electrons. The central carbon that has 4 formal electrons matching its 4 valence electrons, that would have a formal charge of 0. So every atom in structure A would have a formal charge of 0. Let's look at structure B on the right. If I look at the oxygen on the left, we would count out 7 formal electrons, 6 from the lone pairs, 1 from the bond. That would mean the oxygen on the left in structure B would have a formal charge of -1, 1 more formal electron than valence electron. The oxygen on the right in structure B would only have 5 formal electrons. 2 from the lone pairs, 1 from each bond would make 5. Well, we have 6 valence electrons for oxygen, so that means in structure B, the formal charge of the oxygen on the right would be +1. The carbon still has 4 formal electrons for a formal charge of 0. So now formal charge can be used to break that tie. Structure A on the left, no formal charge on anything. Structure B on the right, we have formal charge. Which one is going to be better? Well, the less formal charge, the better. So we would want structure A. Structure B is not the correct structure. We would go with structure A. Now remember, in terms of octets and total number of electrons, both of these were equivalent. We are in a tie situation. We used formal charge in order to break that tie. Less formal charge, the better. That's what had us come to arrive at structure A as being the correct one as opposed to structure B. So the next molecule we want to look at is BF3. And when we think about BF3, we have 1 boron and 3 fluorines. Borons in group 3A for 3 valence electrons, fluorines in group 7A for a total of 24. So when we think about the Lewis structure writing that we would have for this, well, we would definitely start with boron as the central atom. Fluorines would be our outer atoms. You would complete the octet of electrons around each fluorine by making lone pairs, so 3 lone pairs around each fluorine. So we'll put all of those in. And then you check and see how you have done. Do you have 24 electrons? Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yes, you have 24 electrons, so that looks good. Next, you would check for your octet rule. So checking for your octet rule, you'd start by looking at the outer fluorines. And you'd see that each outer fluorine does have 8 electrons in its area, so those are good. Next, you would look at the octet on the central atom, the boron. So you look at the boron, and you'd see you'd only have 6 electrons around that central atom for the boron. 2, 4, 6. So you only have 6 electrons there. So right away you'd be thinking, okay, I want to complete the octet, so I would move a lone pair from the fluorines in to make another bond, because you know how important the octets are. But you might have a little pause in doing that because you'd say, oh, boron. Boron is in group 3A. I know that it's possible for boron in order to have a deficient octet. So maybe it's okay to not have the octet here. You're kind of in a little bit of a conundrum. So what you would do is you would explore both possibilities. So if you did move it in, what would you have? Well, you would have the structure I'm going to write on the bottom. Where we move those in. And now I make my lone pairs. I only have 2 on the fluorine on the left, fluorine on the bottom would still have three. Fluorine on the right would still have 3. So you'd have these kind of 2 competing structures that you would be kind of analyzing. And we'll just label them. The top one we'll call A. The bottom one we'll call B. And you're kind of looking at this and say, we know octet's important, but boron can be an exception. We haven't really clarified what would happen. Here's where you could use formal charge to really pick out which one of these is the better Lewis structure. So you would go through and you would assign formal charge to everything. Starting with structure A. The fluorines in structure A would all have a formal charge of 0. Why would all the fluorines in structure A have a formal charge of 0? Well, their formal electrons would be matching their valence electrons. Each fluorine would have 7 formal electrons. 6 from its lone pair and 1 from each bond. That would give you 7 formal electrons matching the 7 valence electrons for a formal charge of 0. Then for the boron. The boron has no lone pairs, but it gets 1 formal electron from each bond. So the boron would have 3 formal electrons in molecule A. Matches the 3 valence electrons that boron has. So you'd have a formal charge of 0 on the boron. Now if you would do that same procedure with the bottom structure, the fluorine on the right and the fluorine on the bottom would still have formal charges of 0. The fluorine on the left, though, if you count out those formal electrons, the fluorine on the left in structure B, one on the bottom, only has 6 formal electrons. 4 from the lone pairs, 1 from each bond makes 6. 6 formal electrons, 7 valence electrons. Well, it has 1 less formal electron than valence electron. That means the fluorine would have a +1 formal charge. In the bottom molecule, one at the bottom, blue B, if you look at the boron, it has 4 formal electrons. It gets 1 formal electron from each of the bonds. You compare those 4 formal electrons to the 3 valence electrons, you would see that it has 1 more formal electron than valence electron. So choice A has no octet on the boron and no formal charge. Choice B ends up having an octet on the boron but has formal charge. We still haven't really broken the tie here, though, right? Why? Because, well, what does choice A have for it? No formal charge. That's great. And we know it's possible for boron not to have an octet. What does choice B have going for it? Well, what's not good is that it has formal charge, but we know it has the octet, and we know we want to give things the octet usually whenever we can. Choice B gives us an option. So we're still kind of at a tiebreaker scenario, even with formal charge. Here's where we can use that last point about formal charge to kind of break this tie. And that last point about formal charge says the formal charge should be consistent with electronegativity. Well, what does that mean? When you look at the periodic table and you look at fluorine and you look at boron, which one's more electronegative? Well, fluorine is to the right of boron on the periodic table. That means fluorine is more electronegative. It wants the electrons more. So being it wants the electrons more, if fluorine and boron both have formal charge, which one should have the negative formal charge based upon the desire for the electron? It should be the fluorine. Fluorine is more electronegative. It wants the electrons more. Is that what our Lewis structure in the bottom shows? No, that's not what our Lewis structure in the bottom shows. The formal charge of the fluorine and the boron don't make any sense with formal charge in terms of the electronegativity and the formal charge matching. Fluorine has a positive formal charge, boron has a negative formal charge. Well, that's opposite of the way it should be based upon what we know on electronegativity. So the formal charge on the bottom is not consistent with electronegativity. That means that's the final nail in the coffin for choice B. Yes, it has the octet, but it has formal charge, and the formal charge just doesn't make any sense. So that's how we can eliminate choice B as being really in contention anymore. The true structure should be choice A for this, because boron is capable, no formal charge. The other option, choice B, we were able to rule out. The formal charge doesn't make any sense with electronegativity. We can finally rule out choice B, and we can have choice A as our true Lewis structure. So again, you don't want to stress out too much about formal charge, but there are situations like these two examples that we showed, CO2 and BF3, where formal charge can break a tie. If you have two structures that both look okay in a lot of regards, a lot of times what we know about formal charge can have you pick one over the other, like we saw for these last two examples.